So now that we've talked about the structure and functionality of the program, now that we've talked about the visualization of the different phases, it's time to actually look at code, which is the fun part in my mind. So let's go ahead and take a look at the parallel streams implementation in the ImageStreamGang program. So we're going to focus on a hook method called processStream, which is initially designed or defined in the StreamGang superclass, and then refined with the ImageStreamGang class, and then ultimately overridden and customized for each of the different implementation strategies. Here, of course, we're focusing on the parallel stream strategy implementation of the processStream hook method. And this hook method is automatically called back by the framework. And if you go to this link, you can see all this code. The code is actually much better documented than what I'm showing you on the slides, of course. So here are the steps. We get a list of URLs. This getInput method comes from the framework. So the framework knows how to get information from somewhere. It doesn't know where, but it knows that you need to get information. So that's part of the underlying framework. And then we convert that list of URLs into a stream, a parallel stream of URLs. And then we go ahead and we apply the filter intermediate operation. And what we do here is we use the method called URL cached, which we'll look at in a second. And if URL cached returns true, that means that we've already downloaded this image and processed it before. So by negating the result of URL cached, we will filter out stuff that's already been seen. So as a consequence of doing this, the filter operation, as always, might return fewer elements in the output stream than came in for the input stream. It doesn't change the type, it doesn't change the values, it just filters out the ones we don't need. And here's what URL cached looks like. It basically does a little check to see whether anything already exists in the file system with this name. So it's going to go ahead and do an any match. And so if there's anything with that name, we've already downloaded and filtered this before. Here's what URL cache does. It tries to create a file with the name of the image in the file system. And if the image already exists, if image file exists, then we know it's already been downloaded and cached. We could do much more sophisticated ways of image caching here. This is a very simple-minded way. The right way to do this is probably to have some kind of age parameter like you have with normal HTTP with the max age header, and then only allow images to be alive for a certain amount of time before they become stale and have to be refreshed. The next phase takes those non-cached images in the stream and applies map, which will return an output stream consisting of the images that were downloaded from the URLs in the input stream. And remember that the map operation is always going to return the same number of elements in its output stream as were in its input stream, unless an exception is thrown or unless some type of short-circuiting terminal operation is applied later. But in this case, that won't happen. So we should get the same number out as we had come in, except they will have been downloaded, and we will have transformed them. And here's the code to do this. There's a method called blocking download, and it uses this really cool mechanism that we've talked about called the blocking task in order to use the common fork join pool in a way where the fork join pool will be expanded as necessary for blocking operations. So the manage blocker mechanism in the common fork join pool is used for IO-bound operations that need to expand the number of threads in order to be able to keep the system responsive. So that's what blocking download does. Again, we talked about this earlier, the manage blocker mechanism here. And this is just a little wrapper that I wrote to make that cleaner and easier to understand. Keep in mind something important. We don't spend a lot of time talking about this in this course, but in my other course, we talk a lot about this. You typically need to have as many cores as you'll have things that block. And so the question that arises, how many cores do you need? How many threads do you need for a blocking program? And IO-bound tasks on an N-core CPU typically run best with N times 1 plus wait time over service time number of threads, where the wait time is the amount of time you wait for stuff, the blocking time, and the service time is the amount of time you actually spend time doing work once the blocking has finished, once you've got the item you want to work on. So without going into too much detail, if you end up with the service time being low relative to the wait time, you need more threads. basically the bottom line. And a CPU-bound task won't have much wait time at all typically, so you don't need as many threads. So that's a formula that can be used, and there's a nice article here that talks about this in more detail. So now we've ended up with a stream of downloaded images, all of which took place in parallel. And so we then run this through map again, except this time we're going to apply the filters, apply filters, method reference, and that will then do the transformations and also store the results. And once again, there's a one-to-one mapping of what comes in and what comes out, except we're going to do this really clever technique here of using map followed by reduce. And the whole reason to do this is because flat map doesn't work in parallel. So we have to do this kind of a weird quirk. So we're going to have the same number of output stream elements as input stream elements, except that's not really what we want. We really want to have this thing flattened, and that's what reduce is going to do. So here's what apply filters does. So what it does is it takes an image, and for that image, it goes through the list of filters, turns them into a parallel stream. Remember, filters are like, grayscale, sepia, tint, emboss, whatever. For each of those image filters, it's going to go ahead and apply the filter on the image in parallel. And what we end up with here is a stream of images. So for each image that comes in, let's say we have an image that's, an image of the Taj Mahal, and we want to filter it, we're going to get k elements in our output stream, k being the number of transforms or the filters to apply. So apply filters returns a stream of images. So what we end up with here, map comes in with an image, and it leaves with a stream of images. Each element is mapped to a stream of images. Well, that's not really what we want. We really want this thing flattened out, so we just want to have a stream of images, not a stream of images. So we use the reduce method with the stream concat method reference, and that flattens the results out. If flat map worked properly, we wouldn't need to do this particular technique, but it doesn't, so we're stuck with it. But the good news is it's very idiomatic and it's easy to use. So again, this idiom here, map reduce, works around a limitation with flat map, which we've talked about before, and you can read about here in more detail at that link. Now, what's weird is that reduce in this case returns an optional, so we need to handle that case if there was nothing in the stream at all. If there's nothing in the stream at all, which is not the case, if everything was cached, then we didn't end up with an empty stream, so we just return stream empty. But normally that won't happen. So then what we do is we take that stream of transformed images and we collect them into a list. And this is one of the very, very rare times you'll actually see multiple terminal operations in the same stream. So you'll see we have reduce, which is a terminal operation, followed by this or else thing, and then we have collect. So this is really the one that triggers all the processing, and then after we end up with a stream of transformed images, we collect them into a list. You don't see this every day, but it's worth being aware of that. So this will trigger the remaining intermediate operations. The first ones are triggered by the initial reduce. And we again end up with a list of filtered and stored images. And here, just for kicks, I print out how many of them there were, just to give some diagnostics. Okay, so that's the end of the code walkthrough of the Parallel ImageStreamGang case study. And I think it's pretty cool, and it shows you how using functional features in Java makes it a lot easier to write code that is close to domain intent and can also be parallelized nicely.